I am going to give you a presentation on programming for non-programmers and programmers, but mostly I wanted to address the non-programmers so you know what we do. So, who is this for? Say I'm on mechanical, I'm on electrical, I don't need to understand any of this, but I'm on the programming team, and it clearly says for non-programmers. The idea here is we want to give you an understanding of how programmers see the robot, and so that we can have clear lines of communication when we're talking, okay? And that's very important because if you want your mechanisms to do what they're supposed to do, if you want the robot to perform the way you think it should perform, we need to communicate as a team to get that done. So, I'm going to go over kind of how we structure the code, which I think is important to understand because that's how we see the robot. So the way we see the robot is very similar to the way you see the robot with some minor differences. I want to talk about considerations when designing and building the robot for programming, okay? So there are things that CAD, mechanical, electrical can do that makes programming easy, and there are things you can do that makes it hard, all right? And then I'm going to show the methods that we have used on the robot so you guys are familiar with what we do, and if anyone asks, hey, have you guys done this? You can at least talk a little bit about what we've done in programming with the robot. So, I'll review the structure of the code. So, this is a little drawn mock-up of our 2018 robot. It has an elevator. So, we have a little video for the elevator. And it's just like any other elevator that we've done. Now, this should look very familiar. We had an elevator this year, right? But you'll also notice this particular year, I'm just going to point it out. I don't know if you saw the PDP literally under the elevator, so that if the elevator broke, it would crash into our PDP and completely disable the robot. So this is what I'm talking about when you design the robot, design it with programming in mind, because we had to spend a large amount of time making sure that the elevator never crashed into the PDP, because that would have ended the robot right there and then. So, all right, you don't have to click the links for this because it will just take too long. So then we have the drivetrain, which many of you have worked on, right? This year it was tank, but we typically use swerve. Next, we have the intake. Have you guys seen the 2018 game? No. Do click on this. So this will show you what we were picking up that year. Does that make sense? So we're picking up cubes. This is us. There's our intake. There's it delivering. You'll see it come along. You know, what's the methodology that LUNATECS like to embody when it comes to picking up game pieces? What's our motto?
The hardest one we have.
No.
Keep it simple.
Well, that's the mechanism by which we design, but what do we commonly talk about when we see a game piece? We touch it.
We take it.
What? Exactly. We touch it, we take it. We do not want to spend time chasing game pieces around the field, right? We touch a game piece, we pick it up. And you guys have seen many times, we're not always very good at that. You'll see us that we have chased game pieces around the field. And what happens when we chase game pieces around the field?
We waste precious seconds.
Exactly. So, you touch it, you grab it. We had a climber that year. You want to click on the link there so they can see what the climber looked like. The climb that year was interesting. There's this little hook here that you have to grab on, and then you pull yourself up. So you'll see our climbing mechanism. Do you see how that worked? We went up, it came back down, a hook grabbed on, and then detached from the robot. And then very similar to the climb we did this year, right? We went into the cage, we grabbed the cage, it detached, and then you'll see how we lift up. And it just uses a winch to pull us up. It's a very simple mechanism to program. It's very dumb. And I'll explain what I mean by that when we go on more. But basically, you hit a button and it just winds. And it's very easy to program. Mechanically, putting that together was pretty ingenious because this was flexible, this part here, this polycarb. And so when it came up, it could go up. But when it came down, this hook would grab on and then detach. So, and then we also incorporated forks. Why did we incorporate forks?
So you could pick up another team.
Exactly. This year, the amount of robots you got up above a certain level gave you mad points. So lifting up another team that couldn't climb would get us mad points. So here we go. You're gonna see us come. We're gonna connect. We have one fork down. It was a little, the forks weren't necessarily perfect, but we would get them going, and then here we go. So that was our climb with forks. And when the buzzer buzzed, you just had to be above that point. So then after that, if you dropped below it, you were totally fine. Whereas this year it was what, 3 seconds, right? So this year it was a little bit harder because when you climbed and you were off the ground, you had to be there 3 seconds after the buzzer.
Wasn't it when the lights turned off that you were in the clear?
The lights turned off at 3 seconds.
The lights turned off at 3 seconds. So yes, you are correct. It just so happens that they're the same. So when we designed this robot, we broke it down into sub-teams. Much like when we talk about designing the robot mechanically, we have different sub-teams. We'll have an intake sub-team, a drive team sub-team, an elevator sub-team, a climber sub-team, and a fork sub-team. We just break those down into systems for us to code. And then each system, what we do is we detail the motors that are involved in that system or a solenoid. So that year we used pneumatics. Do we all know what pneumatics are?
Isn't it like pressure valves or no pressure, like?
Yeah, like it's things controlled by air. They could be off or on. Yeah. And basically they're using pistons. So there were 2 types of pistons we used on this. The traditional one where it would go out and in, but then we also had these little buttons that came out and in, which were really nice as well. Now we use, instead of using solenoids, we use, what's the motor that we used for the dropping of the servos? Thank you. And they're quite compact and they do a better job. The problem with pneumatics is you have to have an air compressor and air tanks on your robot, and that takes up weight. And they're also a pain to connect.
Also, don't those cost a lot of money?
I mean, I don't know the cost of pneumatics.
You get a bunch in the kit, so you don't have to pay a whole lot up front.
Yeah.
But if you want like the bonus things, they're not like expensive. They're about as much as any other FRC part, so they are expensive, but they're like more so than
like motors.
Or something.
Yeah. So basically then what we do is we will write, based off of the subsystems, we will write commands. And those commands will call various subsystems to do what we need them to do. And those commands will be linked to the controller. Does that make sense? So we have a release fork command, which calls the fork subsystem. We have an arcade drive command, which called the drive subsystem. We have a raise intake command, which calls the intake subsystem, so on and so forth. With these commands then, what we can do is we can link them together to make autos. So an auto is not just calling one command, right? It's calling like 5, 6, a lot of commands. So what we can do is we can make what is known as a command group, and we can say, hey, execute these commands in order. So these commands tend to be the commands that we execute in our autos so that we can reuse. Does that make sense? So that if we find a problem with one of our commands, we just have to change that command and it fixes it for auto, but it also fixes it for teleop. So when we took the elevator up to the proper height to deliver the Coral this year, if that elevator wasn't getting to that proper height, we changed one command, right? And we fixed it in that command, and then it fixed it both for auto and fixed it for teleop. Does that make sense? And this is how we can reuse code. So, speaking of the controller, this is how the controller was. The drive controller, forward, back, left, right for turning. The operator ran the intake command, ran the outtake command to shoot it out. Raise the intake, because the intake could go up and down, because you have to start within the certain frame firmer. Does that make sense? Take it down. And then we also had releasing the fork command required both people to press down on the D-pad. Why do you think we did that? New people. Only new people.
To prevent any accidental releasing.
Correct. So typically you want when you're designing commands or your human interface, you want that to be intuitive, right? You want it to feel natural. You want the operator and the driver to feel like it's very easy to do. However, conversely, sometimes you want things to be hard. And the reason why you want them to be hard, because by accidentally doing them could cause problems within the game. If we extended our forks mid-game, not in the last 30 seconds, but mid-game, we got a penalty, I think, every 6 seconds that we had them released.
Why?
Because you could only reach, I believe it was
18 inches or something.
like 18 inches out of your frame perimeter, which is what our intake did. But our forks released like a yard out of our frame perimeter so that another robot could get on it. But in the last 30 seconds, you were allowed to reach as far as you want. Like there was an extended reach that you could do so you could lift another robot. But if that didn't happen in the last 30 seconds, we'd be in trouble. And you also had to be on that little platform. Did you see the platform that we went up on? You also had to be on that platform to do it. So, considerations when designing and building the robot for programming. This is probably what's the most important thing for you guys to take away if you're not on programming. You want to think like a programmer. So, what do I mean by that? When you design your components, think about how they're going to work together, okay? Think about what you're asking programming to do. 2 years ago, in Crescendo, we were trying to do the trap, okay? Do you guys know what the trap was?
It was where you climb, but you also put a note in a specific area.
Yep.
Got you a lot points in the end game.
So for the new students, I'll draw it out a little bit, but basically there was a chain that you could climb on in the end game, okay? And you got up on this chain, you got some points. But then behind the chain, there was this structure, and it had an opening here. And if you could get the notes, that year the game pieces were called notes, and they were, you've probably seen them in the shop, the donuts, the orange donuts, maybe you haven't. But if you could get one of these in this box here, which was called the trap, you got bonus points. And here's the kicker. You could only reach so high that year. So it wasn't like you could go under this chain, get up to this thing, reach up to it and put it in. That wouldn't work. It was too high to do that. So what you had to do was you had to climb on this chain, get your robot up to a certain height, and then put it in. And the problem was the mechanism that they gave us to do the climbing, the way they envisioned it was we would go under the chain, extend this mechanism, grab onto the chain, and get up. But the problem is no matter how we tried to program it extending, we couldn't do it under the chain. It kept getting in the way. We couldn't trap. And because they hadn't really thought about how it was going to do it, they were able to do it in the CAD. They drew it in the CAD. They're like, look, it's in the CAD. And you just, here, we'll just extend it, we'll put it on, and look, it grabs, it goes up, it's perfect. But they didn't think about how to get from A to B. And so because they didn't think about how to get from A to B, they didn't realize it was nearly impossible for us to come up with a sequence of commands to get it so that it could get to the position that it needed to be in with the chain there. So when I say think about how your components will work, think about how they're going to interact with the field. Think about those base mechanisms to do. Because like that year, we had a shooter on a pivot here, but the shooter could also extend. And then we also had something here that could also pivot. Well, I should have put that in here just to show you, but it could do some really cool stuff, and it did some really cool stuff. It was really fun to watch once we had stuff working, but it also took a lot of time programming it, because we talk about, I don't know if you guys talk about degrees of freedom with a mechanism. Does that make sense to anybody when I say degree of freedom? What does that mean?
The amount of angles that it can rotate from?
Yeah, the amount of movement it can do. This had 3 degrees of freedom. It could turn, it could move here, it could move here, and it could move here, going in and out. Every degree of freedom you put onto a mechanism is more coding that the programming team has to do. And as a result, if there's more coding, what do you think happens?
More complex, more bugs.
More bugs, more complexity, what else? It takes more time. And And when you get us the robot a week before competition and you want certain things done, then autos start suffering. Because if we're working with the base systems and just getting them working, we don't have time for autos. Because we have to get the base systems working so we can play in teleop. And that's how we approach the programming. We will start with, how do we program this for teleop? Okay? And then from teleop, then we move on to autos. Because everything we do for teleop will be reused in auto. So it's not like we're wasting time by doing teleop first. We're just prioritizing playing the game first and then auto second. As I said, think of how they work step by step. The robot is dumb. I think we all know this. It only does what we tell it to do. It can't think outside of what we program it to do. So even though we want it to do X, Y, and Z, it may never be able to do X, Y, and Z because programming smarter robots is really hard. So sensors. Sensors are how we get feedback from the robot. Without sensors, a lot of what you want done can't be done. So you want to think about, why does the component need it and how will it help? If you're putting sensors on a component for no good reason, you're running electrical wires for no good reason, you're making the robot more complicated for no good reason. So only put the exact amount of sensors on the robot that you need, and only the right amount of sensors for the component. And we don't always get this right. Matter of fact, we got this very wrong this year. I don't know, for those who were on the team last year, where did we put our limelights? This is top down. Here's the robot. Here's the elevator. Where did we put the limelights?
On the side?
Draw it. Show me where we put them. Initially, not where we ended up. Go ahead.
Okay.
This is the front. So this is the.
That's not the climber.
That is not. So this is the elevator. This is what holds the coral.
Okay.
And so this is the front.
Okay. Well, we put our limelight like on the elevator, right?
Nope, we did not.
I know we had a mount.
Yes, we talked about that. That was plan 2. But no, so we'll get to that. Do you know where? So does anyone remember where we exactly put? Lydia, do you remember where we put them? Initially, for the first competition, where were they?
Was it right in front of the elevators?
And they designed the robot to do this. They were beautifully placed. We were so excited.
Were they on like either side?
Exactly. What we did this year, what we thought was the right thing to do, is place 2 limelights that were 6 inches off of center from the center of the robot. Why did we do 6 inches off of center? I'll give you a hint.
Because that's where the reef.
That's where the reef posts were. So we were going to use the limelights to center in on this April tag, okay? And then when it approached, this would be 6 inches off of center, so that if I'm using this limelight here, the limelight would end up here, our elevator would end up here. Does that make sense? Seems like a good plan? Ronan's falling asleep. Do you remember what happened when we started lining up?
Wasn't it like after we got to a certain point, we would just completely lose sight of the April tag?
Correct. So what happened was, as the robot approached the April tag, there came a point where we could no longer see the April tag. And in those 2 inches in lining up, we would get off center. And it happened again and again and again. It was a flawed approach. Then we tried saying, hey, let's put it on the elevator. That wasn't going to work because it couldn't see over the coral. So what do we end up doing?
On the side?
Put it on the side with an angle so that even when we were all the way up and touching the reef, we could still see the April tag. And we will go over later how that works and why that's important. And but I wanted to, when we talk about it, we don't always get it right. And when we get it wrong, this was painful. Because I know Micah and the CAD team spent hours trying to find out where it could go. And it took programming hours of researching, what if we put this on an angle? What if we put it back here? Could we still use it the way we thought we could use it? And we couldn't use it the way we thought we could use it. We had to use it a completely different way. But we eventually got it there. And that took away from things like building a climber, right? When did we get our climber put on the robot? Worlds. Wouldn't that have been awesome? That particular climber, wouldn't that have been awesome to have at District Champs? Yeah. We were messing around with a sensor so that we could line up. But how important was lining up to the reef?
Not, it was very important.
Very important.
Very important. You put that as like a high priority, needs to happen, cannot go forward without this working. And how did it work in teleop and auto when it was finally working?
It worked great.
Worked great, because we spent a lot of time doing that. But we didn't get a whole lot of time on a climber. We tried various iterations of climbers, but we weren't putting the whole team behind the climber. We weren't having programming think about it or CAD, it was, well, we think this will work, right? So, all right, limited time. I'm already alluding to it. We have limited time. Keep it stupid simple. A lot of people like to say, keep it simple, stupid, saying that you're the person that's stupid, but there's not a stupid person in this room. You all are very intelligent people. So what we really want to say is keep it stupid simple so that a stupid person who's not in this room could understand what you're doing. If you do that, your mechanisms will be simple, our coding will be simple, and the ability to get it done quickly will be done quickly, will be achieved. And this will be true, I think this is true across electrical, mechanical, CAD, and programming. I don't think any of you would disagree with that, correct? So what's true for you guys is true for us as well. More complicated the component in terms of sensors and motors, the longer it's going to take to program. So if you give us a very complicated mechanism from CAD and mechanical and electrical, have a very good reason why you're doing it. And there are good reasons to have complicated mechanisms, right? But if they don't have to be complicated, if they can be, instead of 3 degrees of freedom, 1 degree of freedom, let's do that. Right? I'd rather a simple mechanism that delivers 90% of the time than a complicated mechanism that delivers 100% of the time. Unless that 100% is critically important. Does that make sense? Look at our elevator. I mean, and our mechanism for delivering the coral. How many degrees of freedom did that have? It had 1, right? Just the elevator going up and down. And the angle at which we held the coral could deliver it on 3 levels, right? 4, 3, and 2. No problem. Never had a problem. We could have built in an angler to give us that last level 1, and we could have delivered it on level 1 using, if we could adjust that, how that went. But instead, what do? We built it on the front and had a completely separate mechanism. And we had the space for it, so we did it, right? You know, what do you want us as mechanical and CAD and electrical, what do you want us to spend our time programming?
The robot's movement.
Okay, for what? Well, I mean, like if we don't even know what the next game is, but what would you want us to spend the most time programming for next season?
Driver's work.
Okay, but let's say we get that done pretty quickly. Then what do you want us to work on? Yeah.
The driver, or the robot.
Well, yes, of course, that's what we're programming.
But like the robots, like the yeah.
The what?
Like basic functions of the robot.
Well, basic function of the robot, if we follow these principles, will get done pretty quickly.
Like the consistency and efficiency.
Consistency, efficiency.
The shooter.
Well, we don't know if we're going to have a shooter. Go ahead, Mark. What? Precision? I think what you're alluding to is you want it to be able to do what it does. Do you want us to work on autos at all? Autos? How important do you think autos are in FRC? If you had to, how important?
Pretty important.
Top teams in the world. How good are their autos?
They are amazing.
Spot on.
Amazing, spot on.
Keep
5.5
teleop.
piece.
What?
They're so good, they keep them going into teleop.
If I start coming out of auto with 60 points this year, how am I going to do in teleop?
Pretty well.
So one of the things that you probably want us to spend a lot of time on autos and not the basic functions. If the basic functions, this is meaning that the basic functions are working the way they're supposed to work, right? If we have to spend time on a basic function, we'll spend that time on it to get it perfect, all right? But it's the action economy like in video games. You all play video games? So have you all played like RPG video games? Maybe a game that has like magical spells and whatnot?
You play Dungeons and Dragons?
Oh yeah.
So you only have a limited number of actions you can do in a certain amount of time, right? So when you're playing with the action economy in a video game, you're going to want to sit there and be like, okay, Maybe I can cast 3 spells that do 10 points of damage or 2 spells that do 20 points of damage. Which one am I going to do?
2 spells.
Because that's 40 points of damage as opposed to 30 points of damage.
That's 1 less turn.
And it has 1 less turn, right? So you want us to think about, we only have limited time to program everything. And so we literally in programming will kind of categorize our mechanisms or our subsystems from like just dumb subsystems to complicated subsystems or subsystems that need precision. So like a subsystem that needed precision this year was the elevator, right? Do you think the climbing mechanism needed precision this year?
Yeah.
Yes.
You'd be wrong.
Not that much. No, it didn't. No, it didn't.
I mean, it needed precision to line up, ask any driver. But once it connected, okay, there were 2 mechanisms on the robot. There was the servo that you hit that dropped the what do you call it? The thing that took in the coral from, what? The feeder, that dropped the feeder. 3 things. Then you drop the climber. That was also pretty simple. And then when you connect it on, we just ran a winch that just pulled in the string and it just lifted the robot. It was very simple to program. Matter of fact, I think we spent maybe less than 20 minutes programming the whole thing.
Wow.
Now, how long did we take to program the elevator? How many?
Like a couple meetings.
There were several. Literally, we sat there going, "Oh, are we at height? Are we not at height?" And we sat there and programmed and programmed and programmed and precisioned it and got it right. And that paid off. I mean, we got picked second at Worlds and got to play because of how good our robot was. So you want us spending time on the things that need to have time spent on them and less time on the things that don't. I think that makes sense, right? What are we looking at for time? Oh, I'm doing phenomenal. Oh, okay.
How many slides is it?
40 slides.
Oh, I thought you were about to say 400.
No, but it's growing. It's growing. It had 10 more than it did on Thursday. So I added 10 more slides on Thursday. There's no way this thing shrinks. I wish it could.
Can you add like every subsystem as a slide each one?
That would be insane, but yes.
Yes.
I could. So I think I've mentioned this. Sensors cannot be an afterthought, okay? They need to be designed into the component. You want to use as many sensors as you need, no more, no less. If we do not get the sensors right, we're going to spend weeks trying to rejigger where those sensors go. There were many sensors that were afterthoughts this year because 1, we didn't think about it, but 2, we were watching what other teams did and we're like, oh, that's actually really good. Can we put a sensor there? And I think I made Nate's hair go gray because we were asking to put sensors in places that just weren't designed for sensors. And Nate figured it out, but it took him, 3 meetings to figure that out. And if we're spending 3 meetings figuring out where a sensor goes, what are we not doing? We're not programming, right? Because we need that sensor. So we need to be very deliberate about where we put our sensors so that mechanical and electrical can be deliberate about building them there. And I know that sounds weird, but the reality is if there's not a sensor where we need a sensor, you need to run electrical to that sensor. You need to run the CAN network to that sensor. Who's on electrical? Okay, so all of you, if I were to say, hey, I need 20 sensors at the top of the elevator when it's fully extended, how much do you want to get a baseball bat and beat me at that moment? Yeah.
I would like to politely lie you down.
I mean, that's complicated. That's not an easy thing to do because you got a lot of things like, think about it. You got this mechanism that's going up, 7 feet, right? So you got to have all that wire, 7 feet of wire, and you got to get, we'll just say 5 sensors up there. So you need to run 5 sets of electrical, which come in 2 pair, right? A red and a black. You got to run 5 sets of CAN. Well, you probably get away with 2 sets of CAN and then and daisy chaining them up there. But that's a lot of wire. And that wire then has to extend and retract. It's not easy to do. And if we do it at the beginning, if we say, hey, when we're designing the robot, and we're going to do this at the beginning, it's a lot easier, right? Because you can then lay out the wire at the beginning. putting the wire into the hose mechanism or in the extending mechanism after the fact is a pain in the butt. So we really need to be deliberate about our sensors and what we need and what we don't need. One thing that we do, interestingly enough, is on every elevator mechanism, we always put a sensor at the bottom of the elevator. Why do you think we do that?
So it doesn't crash into the bottom of the robot if anything important.
Well, how would a sensor do that?
It would send a signal to stop the elevator system.
Yes, but there's a but on that. You are correct. Go ahead.
It'll see how far away it is from the bottom of the robot. And then
So that's not the type of sensor we usually put, but we've tried that, and that's kind of fun. Usually we put a limit switch, a magnetic limit switch, and what we'll do is, as we're bringing the elevator down, we'll bring it down to about like 1 or 2 inches as fast as we can, and then those last 2 inches, we'll just slowly go until the limit switch is triggered, so that, again, we don't crash into the bottom of the elevator. It's a little complicated, but it's not terribly hard. And the benefit of that is we're not slamming the elevator down. Unfortunately, we do slam the elevator up, and Micah will tell you about that in detail. So I can't help that, but I can help it from crashing into the bottom. Types of sensors. So go back. Damn it, they already saw the answers.
wait, what answer?
Exactly. Exactly.
No, I think we're one.
Yeah.
Something's stopping me. Yeah, I don't know. It's not working.
What type of sensors are there? And I want to hear from you guys.
Hold on, wait. What are we talking about?
So what type of sensors are there?
Oh, wait. They're on the robot?
In general.
Oh, motion sensor?
Okay, we have, motion sensor.
I don't remember the exact name, but it's the one that like sends a signal out and then kind of like echolocation.
Rangefinder.
Yes.
Oh, limits.
Hold on. I'm going to go around the table. So
Oh, you said one.
the rangefinder?
Yeah.
Do you want to try to guess another one? Did you hear what Gabe just said?
No.
Oh, you got to pay attention. Mark.
Gyro?
Yep, gyro.
Limelight.
Limelight. Yep.
I think it skips Lucas.
Oh, did I skip Lucas?
Color sensor.
Color sensor. Yep. Anything else? Anybody?
A light sensor.
A light sensor. Like it can determine like brightness? Yeah. I don't think I actually have that one listed, but that is definitely a sensor you can have. And I could see where it could come in really handy too, in various situations.
Ultrasonic.
That's a rangefinder. That's a rangefinder. Now you can say the one that,
Limit switch.
a limit switch. What's a limit switch?
Once it hits a certain point, it'll switch how things work for a second, and then once it reaches another point, it'll go back to normal.
Yeah, so it's an off and on switch. So basically think of it as like a light switch. And if like you have a mechanism that hits it, it's on, the mechanism releases, it becomes off.
Pressure sensor.
A what?
Pressure sensor.
Yeah, that's one I haven't listed either, but that is one we could do. All right, let me see what I got listed. So, motion sensor measures motions. A motion sensor is actually really cool because you can use it to, we used it 1 year, or it was really a proximity sensor, but we counted the number of balls that we had in the robot. So you only could carry 2. So we only ever wanted 2 balls in the robot. We wanted to tell the drive team that they had 2 so that they could go and shoot the balls. Gyro, what's the gyro do? It gives you balance, heading, drift, right? The problem with gyros is they will drift over time. So whatever their setting may be, will drift over time and you have to reset them. If you're ever resetting swerve, that's why you're resetting. A color sensor. There was only 1 year that FRC wanted to use a color sensor and then the game got canceled. That was due to COVID, yes.
Thank God for COVID.
I kind of wanted to see where this would have gone because, it was so bad. Yeah, there was a color wheel and you had to spin the color wheel so many times. And then like whatever color it landed on, you had to do a thing, like it was bad. Yeah, be grateful. Limit switch, so they're off or on. No one mentioned encoders. Do you guys know what an encoder is? No. This is actually this is the sensor that we use the most. Go ahead, someone.
Counts the rotation of a motor.
Yes. So if it used to be different. The motors now count in whole numbers. Well, they do fractions, but if Yes, Mark?
There would be one inside of a servo.
Yes, there would be one inside of a servo motor. There's also in every Falcon and Kraken, they also have encoders. And they count, for every rotation that the motor does, it counts 1. So if it rotates 3 times, what's the encoder's value? If it rotates 4.5 times, what's the encoder's value? And if I hook that up to gears, right? If I hook that up to gears, we just had the gear assembly, let's say it's a 4-to-1. How many times does the mechanism rotate on a 4-to-1 if I rotate 8 times the motor?
2.
Correct. Did I get that right? Yeah, thank you. I am not mechanical. We will record the gears in our subsystems because when we are doing extensions of the elevator, we don't count encoder values, we count height. So we will convert, for example, how high the elevator is going into inches. Because what is everything in the game manual in?
American.
What?
American.
Well, yeah, it's in inches, right? Like it's in measurements. They don't say, oh, it's this many rotations on a motor that is geared this way. They say, listen, the top of the net for the algae is 8 feet off the ground, right? So it's 96 inches. So, you know, we want the elevator to go X high. In this case, we didn't actually go above it. We went right up parallel to it because we had a really kind of neat mechanism of just rolling it in real nicely, right? But like, how high was the top reef? Does anyone remember?
Was that like 14 feet? No, not 14 feet, definitely. 7?
I think it was 6 feet.
6 feet.
Maybe 7 feet.
Yeah, so like we had to go 6 feet, but we had to go above 6 feet because we're shooting down onto it, right? So we went, I think, 72 inches or something, 74 inches. So if we went 74 inches high, we could drop real nicely. And we'll also start, we also will start where the mechanism is off the ground too to get that height. So encoders help us there. They also help us with our swerve. And we'll talk about that. Limelight is a camera, but the Limelight is a really smart camera because it can look at April tags. It can also do object detection. So it can detect objects on the field and classify them. They can say, hey, I'm looking at coral. Hey, I'm looking at algae. And we can do things with that. Proximity sensor is another one you guys didn't mention, but that's kind of like a motion sensor. It's kind of like a limit switch. But basically, it will detect if something is within a certain amount of distance of it. And we've used these before as well. They're really nice.
I thought that was somewhat of a...
It's like a rangefinder. It is. You're not wrong. And we've actually turned rangefinders into proximity sensors. I actually prefer, instead of getting a proximity sensor, I'd rather have a rangefinder and say, hey, do I see something within X inches of me? We did that this year. Where did we put a rangefinder on the robot to make it act as a proximity sensor this year? Does anyone know?
At the top of the,
We did that, but not that one. That's not the one I'm thinking of. Because we stopped using that. What's the one that we used for the entire season?
Probably one for the bird feeder.
Right. So if this is our coral intake, right? And the coral comes in here. We had a proximity sensor, a rangefinder, at the very end of this. So that when it came and it saw that, what did we do? What do we do when that proximity sensor, because what happens if I'm running the motors on here, right? My motors are pushing the coral into, what happens if I don't stop? What happens to the coral? We'll just shoot out, right? Like you go up to the human player station, you drop a piece of coral in, what's gonna happen? It's just gonna shoot right out the robot. So we needed some way, go ahead, Mark.
So when it gets close enough to it would stop.
It didn't quite stop the motors. We did a little sequence, but yes, essentially it was there to stop the motors. So what we did was when this rangefinder saw something within 2 inches of it, the opening was, I think, 4 inches wide. And when it saw something within less than 2 inches of it, it ran the motors backwards and stopped them. So it ran it backwards for like a half second. I think it was like a quarter second, right? It was very quick. But we ran it backwards and then stopped the motors so that If you saw it shoot out a little bit, it would like suck it back in and then stop. Next. All right, so what we do is wherever we have sensors, we will put them with our subsystems, because typically those subsystems have those sensors for a reason, and when we're using those subsystems, we're going to read those sensors to be able to do things with it. So in our code, we organize them as such. Much like where you would put a sensor would be on a subsystem in the robot. What time is it? Good. Okay. Next. All right. So we're gonna have a little exercise. Oh, I am old, so I will not be bending down. And we've done this for the news. Who was here last year when we did this? Raise your hand.
I don't even know if I was like, I probably wasn't paying attention last year, so. You're true, nothing has changed.
I know, it's because it's the same program. So we're gonna build an auto. You guys are gonna be my sensors and my code. We're gonna start with Lucas, and each one of you is going to give me a command. Okay? I am your robot. I need those 3 balls inside that bucket or postal service carrier. And when we get to Lydia, we'll go to Mark and then come back to Hannah. So I don't want to leave Mark out. So you are my code and sensors, because you're using your eyes as sensors. Eyes are sensors for a robot.
So do I just like tell you what to do?
Tell me what to do. You give me one command and I will do it.
Go forward, stop.
Nope, you can't do that, because you can give me one command. Gabe, you're next.
180 and stop.
180 and stop 6 feet. All right. Oh, actually, if you're doing 180, technically that was 2 commands, but I'll allow it.
Reach out your right hand
Okay, that's.
to the side, closer to the ball.
Oh, okay.
And back a little, and more level, like right above that ball right there.
Like, what do you mean?
This guy's trying to make it difficult.
This is reaching out. That this doesn't mean anything.
Reach out with your arm more backwards. Position right above.
More backwards, okay.
Position right above.
I know where the balls are.
Okay.
A robot doesn't know where the balls are.
Arm out 6 inches to
45 degrees. Yes.
Okay.
Put your arm down and
All right.
move a couple inches to the right.
What's a couple inches? You can get what? 3?
Oh my.
I'm not kidding. 3. Oh God, I'm now getting a cramp. I am being but you need to be more precise. So we'll go next, Gavin. We'll just assume I'm doing that because it hurts. I'm old. I will let everyone do a reset, and I'll go back to the beginning.
Oh,
The
please.
right.
How?
Now the ball move.
Reset.
You can put the ball back.
Does that make everything you're going void now?
Well, I mean, kind of. All right, who said reset? Okay, I'll let you start over again.
Move forward 3 feet.
All right, what's 3? Okay.
Turn 9 degrees to the left. And move forward 4-ish steps.
Describe for
4-ish. I mean, I hit the wall. You can strafe.
Can we reprogram Mr. Will?
Move like 1 foot to your right.
You give this man a limelight.
Are we running Mr. Will OS?
Oh, it's Mark. Yeah, aren't you glad now? Because that was crap.
Place it on one of the balls.
What?
Place it on one of the balls.
How do I do that?
Robot, where are the sensors?
The robot doesn't know where the ball is.
Okay, I understand. Move it forward 5 inches.
What? Move what? Which one? 5 inches? That's about right?
Do that with your other.
Left hand, 5 inches forward? Okay, I'll give you that. Next, Annie.
Mr. Will, order us pizza. Ooh, can I get pizza?
Close your hand.
I wish this was a balloon.
Do you want to pop it?
Okay. Imagine I'm crushing this.
forward like 5 feet.
5 feet, okay. 1, 2, 3, 4, 5.
Straight to the side, one foot. Yes, it's yours now. Move forward 1 step. Lucas.
You can come over here and look and see what you're seeing. You don't have to sit there.
Reach your arms up.
Gabe.
Drop your, drop it.
Let's try.
What does he do with his arms?
Release hands.
Move your arms out. We have 2 more.
No.
Wait, I can get.
Okay.
Define that as function and then run function 2 times.
Oh, dear God, no. Well, actually, what would happen if that was defined as function?
You would.
No, I would run it. I would run it. I would run it for where we're at. So then all of a sudden, Ronan gets crushed. You just crushed Ronan. Ronan's now in the hospital.
Excuse me?
Yeah.
Oh, okay. So reset. Oh, that's true. You did do a reset at the beginning. Do you want to do the next 2? Does anyone want to try it by themselves?
Yes.
Get till 12:30.
Okay.
12:30.
Okay.
Okay. So move forward. Again, 5 lines.
No, like the same.
1, 2, 3, 4, 5.
Okay. Turn 90 degrees to the left.
Okay. Ooh.
Walk forward 3 steps
1,
until
2.
you. Yeah. Walk the
Play Uptown Funky World.
Okay.
Okay.
Move your arms, both arms, each forward 3 inches. Close arms together. Lift hands forward.
Forward, like you can say
Make
to
them
the. You can say 90 degrees.
Okay, 90 degrees. Rotate 180.
Someone move the. Did someone move that?
No, I think you.
Walk forward 6 steps.
Oh God!
Yeah.
Back up 2 steps.
You're encouraging it.
Move forward 1 step. Move directly to the right 1 step.
Straight fake.
Okay. Forward a 1/8 of a step.
That was good.
Open your hands and separate them.
The funny number.
Anyone else want to try?
Yeah, sure.
Nope, absolutely not. I have a question.
Yes.
Because we're also the sensors, could we just say move forward until you see yellow directly?
I mean, that would be. I mean, he doesn't have 360 vision, so.
I don't have the sensor. You're the sensor.
Yeah.
Mr. Roll,
But could,
move forward until you see black in the background. Well, move forward until you see hex code number 3714F12.
I mean, theoretically, on the robot, if we had a camera that was off to our right, and we were driving, we could program that. So there is a problem with that, though. So when we're programming the robot, we can only read our sensors 50 times a second. Now that seems like a lot, doesn't it? But 50 times a second can be 2 inches on a moving part. It can be inertia. So what could happen is we're going, and the camera, because we're going so fast, takes a picture here and takes a picture here, but doesn't take a picture when it's directly to our left. And then that can cause a problem because we never see the ball. Because in the time that the camera's recording, we don't see it in our processing. A lot of times what we like to do is we like to get it in sight. So we could have a camera here that's seeing kind of, instead of directly to our left, maybe it's seeing more on an angle. So we get more, and then what we can do is we can direct it to be like in the center of the camera. And if we miss a sensor, we can back up and get more precise and slow down. So the slower the robot goes, the more precise it can be. We'll talk about this when we get to PID loops. The faster it goes, the harder it's going to be. So if we were going really slow and I had the camera here, chances are I'm going to see it and I could stop fairly easily. But if I'm going really fast and I want to stop the robot, what are things that are working against me when I'm trying to stop the robot? Friction. What?
Friction actually helping you stop the robot?
It is actually helping. But what would be the biggest contention? My inertia, right? So that's that. Like once you start moving really fast, if you were to slam on the brakes, what happens in a car when you're going really fast? You slam on the brakes. What happens to you? You go forward, right?
The robot would probably flip over.
The robot can flip over, right? Right, and so that inertia is what prevents us from stopping on a dime. So when we do motions in the robot, what we tend to do is we go fast initially really quickly, and then we start slowing down as we approach our target. All right, next. This is probably quintessentially the most important part of this presentation. We need to communicate. CAD needs to communicate with programming. Mechanical needs to communicate with programming. Electrical needs to communicate with programming. Programming needs to communicate with CAD, mechanical, and electrical. We are all responsible for building this robot. Do not silo yourself. Do not go off into a corner and design a robot without talking to programming, or mechanical or electrical for that matter, right? Like if you design an elevator with no places for wire and you want sensors at the top of your elevator, is electrical going to be able to give you an elevator with sensors at the top of your robot? No. And if we need sensors at the top of that robot, CAD best be putting places for wires on the robot, right? This is quintessentially the most important thing. We need to communicate as a team. We need to communicate constantly. As your mentors, we are working on ways to improve that communication. How are we working on improving that communication? What have we told you we're going to do this year?
Appoint the specific person.
We're going to have specific leads, right? That lead is going to be responsible for talking to their team to get all the information that they need. And then those leads are going to talk amongst themselves to communicate the needs of their team, right? How else are we working on improving communication?
Well, like if we have project management, it'll be easy for every system.
Exactly. So we'll have a project management system. We're using, what's the system we're using, everybody? Shortcut. And what's in Shortcut? There's going to be stories and epics and all sorts of things. So you can go in, just because you're on mechanical or programming, doesn't mean you can't look at other people's stories to see what they're working on, to see what they're designing, to see what they're building. Doesn't mean just because you're on programming, you can't walk into the shop and take a look at how the robot's being built. Matter of fact, for my programming students, one of the best ways to see what we're going to be programming in the upcoming season is to go in and look at that robot and see where are they putting motors? How many motors on the subsystem? Did I not have you do that the other day with the demo bot? Yeah. And we can lay that out and start sketching that out on the board. That's what programming will do. We will go and ask mechanical students, hey, you're building an intake here. How many motors is using this? What's the gear ratio? How's this going to work? Is this going to be extended? Does this extend during the match at the beginning of the match? Does it extend at the end of the match? Is this going to go up and down? Does it even move? These are questions that we need to know, because you know, if it's going to extend at the beginning of the match and it's going to come down and stay down for the entirety of the match, what's the first thing in auto we're probably going to do? If I have a mechanism that has to come down at the beginning of the match, what's the first thing in auto I'm going to do?
Put it down.
Put it down. Exactly, because this is going to dictate how we run the robot, right? You'll notice in Crescendo, the first thing we always did was drop our mechanism for picking up notes at the beginning of the match. As a matter of fact, during auto, we never lifted it up. We just left it down and running the entire time, because it was easy. You get it down, you start it running, picks up notes, we're good to go. So, next slide. I have a half hour.
You got another 22 minutes.
Okay. Good. So, I am going to detail to you the methods that we have used on 316. There are other methods that have been used by other teams. We're not opposed to using other methods for programming, but these are the ones that we know well. And so we kind of stick to them. And then when we try to pick up new methods, we'll pick them up in the off season. I don't like to try new methodologies necessarily out during build season, but we've done that with varying success. Because when you start using a new method on how you program the robot, you inevitably will break the robot. But that's good practice for mechanical, right? Every time we break the robot in practice, all we're saying is we're just helping the team learn how to rebuild the robot. So, PID loops. Does anyone here know that's not on programming or have done programming know what a PID loop is? So, you've done programming, you don't count. At the bottom of everything that we program on the robot, it's either dumb or is using a PID loop. And PID loops stand for proportional integral derivative. Has anyone taken calculus? Do the terms integral and derivative mean anything to you if you're taking calculus? So those are calculus terms. Does my programming team do calculus on the robot? No. However, because FIRST recognizes we are not college students, we are not robot professionals, what they do is they abstract the higher math from us so that we don't have to worry about doing derivatives, integrals, and things of that nature, okay? And so what we need to know is why we use a PID loop. What is a PID loop? What does it do? Why is it important? So not many of you have driven, but you all understand the concept of cruise control, right? Yeah. So what happens? I'm driving my car and I go, oh, my foot is really tired from hitting the gas. What do?
So you press a button that keeps the cruise control at the same mostly the same speed.
So I pick a speed that I want to go, right? Let's say I hit cruise control when I'm at 0 miles an hour and I set it to 60 miles an hour. What's going to happen to that car?
That's gonna rev up.
It's going to rev up real quick. It's going to go super fast. It's going to put a whole lot of motion in it. It's going to go up. What happens as it approaches 60 miles an hour? It slows down. And then when it hits 60, what does it do? It just cruises at 60, right? What happens if it hits a hill? It stays at 60, but what does the engine do? Like it hits a hill, what initially happens? Right, you'll notice if you hit a hill on cruise control, it initially will start slowing down. And then all of a sudden you'll hear the engine rev up. And what's it doing? It's applying power, but pressure is the same. And to get it so it gets to the top of the hill, right? When it comes down that hill, what happens? And now maybe it starts going too fast. What does it do? Starts to slow down. So that is all done by what does that even mean? So when it comes to PID loops, we look at error versus time. You're like, what the hell is error? I'll tell you what error is. In the example we're going, what was the speed we set cruise control to? If I'm at 0, does anyone want to guess what my error is?
60?
Exactly. In miles, 67. We're going 67. Do you know what song that comes from, young man? There's a Philly, I don't even know. There's a Philly rapper who says, in one of his songs, he's like, I'm sitting here sipping away something. I'm not going to tell you what he's sipping. And you're getting 6-7 on the freeway.
Does he just say?
No, he says you're getting 6-7 on the freeway, which is a Philly code for something. He's a Philly rapper, but I won't tell you what the code's for. What? Anyway, that's according to some dude on the internet that has a degree in linguistics. I'm not saying it's true. I'm just saying what I heard. But anyway, error is simply whatever your target is, in this case, 60 miles an hour, versus your current position or your current state. Does that make sense? So if I'm going 20 miles an hour, what is my current state?
What?
If I'm going 20 miles an hour, what is the current state of the car?
Oh, is that 40 error?
It's 40 error because the current state is 20, and you subtract the 2, and you get your error. So if I'm in my cruise control, and the car accelerates and then slows down, what happens to error over time?
It gets smaller.
Right. And the way we do this is by using proportional. It's our first part of a PID loop. So what we say is we take our error and we multiply that by a number, okay? So if I'm using miles per hour and I want to give power to the engine, we'll talk about the engine working at 100% versus 50% versus 25%. Does that make sense? So what I could do is I could multiply the number by, say, what? Let me think about this for a second. Let's say I want to go, I'm going to make it easier on myself because I'm lazy. Let's say I want to go 100 miles an hour. There we go. I can multiply it by 0.01. So if I'm at an error of 100, meaning what would be my speed if my error was 100? 0. So if I'm at error, I can multiply that, and what would I get? 1. And we'll represent 1 as 100%. Okay? So now my car speeds up. It's 100% power to the wheels. I take another measurement. I'm now at 50 miles an hour. I times it by 0.01. What's that value?
0.5.
Now so when I get to 50 miles an hour, I'm going to start slowing down the car. I'm going to say, hey, only give the engine 50% power. Does that make sense? So as I keep sampling this, I'm now at an error of 25. What happens when I hit 100?
Zeroes out.
Zeroes out. We'll talk about the implications of that. But what would, in theory, what would happen if you zeroed out the engine? Gave it 0 power?
It'll die.
Well, I mean, it won't, but it will stop giving power to what?
The car.
The car, and so the car will start slowing down. But if you have cruise control on, what would happen if the car started slowing down?
It'll speed up to compensate.
Right, because all of a sudden now the error becomes 10 because it starts slowing down. It was at 100 miles an hour. We stopped giving power to the engine, and now it slows down to 90 miles an hour. What's the error when it's 90 miles an hour? 10. Multiply that by 0.01. How much power do I give to the engine?
90%.
No.
9%.
No.
0.09.
10%. I times, if my error is 10, and I'm timesing that by 0.01, what is that? 0.1. And then you convert that to a percentage, that's 10% power. So what ends up happening is I can get into this weird up and down, up and down, up and down. No power, power, no power, power, no power, power. It happens. But essentially, we've achieved our goal. We've gotten up to 100 miles an hour. It's giving little bursts of power and keeping it at 100, right? What happens if I hit a hill?
They're going to speed up.
The engine's going to be going a lot faster than the actual car.
Or let's say I hit something like
A wall.
not a wall, but let's say when I start up, I have my wheel here and I have a block here, and I have it so that the engine's gonna, instead of 0.01, maybe I'm timesing it by what? Let's say I don't want it to go at 100. Let's say I don't want it to go at full speed. Like I don't want it to go at 100%, because 100% maybe it hurts the engine, whatever. So let's say I times it by 0.001, which gives me, it doesn't accelerate it as fast. It's a slower acceleration, right? Because if I'm at 100 error, now I'm going to be at giving it 10% power. Does that make sense? Because when I'm at 0, I'll give it 10% power. But let's say I have a block here and it's preventing me from moving. How do I compensate for that? If that block can hold off 10% of the engine's power, will I ever move? No. Not in a bazillion years will I move. I will just sit there until that block deteriorates over time, which could take centuries. Say it's concrete or something. So we can use what is known as integral, and that is our second component. So if we have proportional, that gives us our initial power. We can add integral to that. And what integral is, if over time, so let's say something stops, like at this point, something stops me from getting to my target. Block, let's say I'm going distance, who knows, right? But something blocks me. I can take the area under this curve, right? Like, you've all done geometry at least. We all know what area is. If I were to ask you what the formula for an area of a square is, what is it?
Length times width.
Well, yeah, but so rectangle is length times width, and a square it's side times side, but that's length times width as well. Or length squared, right? Well, you can do in calculus, one of the things you can do is area under a curve. And you're given a formula for a curve, and you can calculate the area under that. So over time, if I'm using proportional, right, what happens? It approaches 0. And then when I get here, my error is 0. But over time, what happens if I if I'm calculating over time the area under this curve, I'm going to have a number for this, right? Let's say this is 1 second. At 1 second, the area under the curve is going to be what this basically almost rectangle is, right? At 2 seconds, it's going to be this rectangle plus this rectangle, right? 3 seconds, 4 seconds. What's happening to the area under the curve?
Smaller.
It's getting smaller, but in each portion it's getting smaller, but totality in its total, it's getting bigger, right? Because this, right, is smaller than that, right? You agree? This here, this area here is smaller than this area plus this area, right? Anytime I add area to something, Gavin lives in a parallel universe. And Now, mind you, over time it's adding less each time, but it's still adding to it. So over time, if I get stuck, what happens to the area? It keeps growing, right? So I can have another integer that I times by this area. Usually it's very small, something like on the order of, if we're doing 0.01, it would be 0.001. So does anyone know what an order of magnitude is? So when we talk about orders of magnitude, so 10 squared, 10 1, right? 10 to the 0 is? 1. 10 squared is, 10 to 1 is? 10 squared is?
100.
10 cubed is? Those are order of magnitudes, right? They're 10 times greater than the previous version. So usually when we're using integral, if we're using I in the PID loop, we will make it 100 times less the value of our proportional, whatever that proportional may be, because this too is going to add power. So what will happen is over time, if this gets hit, our error is set at 10%. It's not growing, right? The error is 10 or the error is 100. We're timesing it by 0.001. Over time, that's still going to be 10%. But the integral will keep growing over time. And eventually, it's going to start adding more and more power. And when it finally reaches a tipping point, it's going to get over that hump. So
You got 4 minutes.
I'm going to first show you a proportional. Click that. So we are right here, and it's very badly, but look at how it does a little wibble wobble there. And then finally it hits the target. And if I go back, and you'll notice something. What happened when I overshot the target?
It wobbled back
Why did it do that?
because it was trying to align with its target.
But it did that automatically. What happens if I dip below this line?
It has to go in reverse.
Why?
Well, it has to subtract power from it.
Yes. So if my error is -10, and I times that by, or -100, and I times that by 0.001, I get -10%. If I give -10% power to the engine, or to the motor, what does the motor do?
It shuts itself down or puts it in reverse.
So when we talk about motors and giving power to the motor, we can give it power, positive power, which will turn it one way. And if I give it negative power, it will turn it the opposite way. So if I overshoot my target, it will naturally correct and back up because I'll now start giving the motor negative power. And negative power means go backwards. Does that make sense? Now, I'll show you what a P can do. Click this one. So we are here. There is a cable carrier here. Watch what happens as it starts turning. We start turning, we stop. We're not fully turned, and then look what happens. We're slowly turning, right? And then we finish our routine. What do you think happened there?
It sensed for a motion bump upwards.
Nope, didn't do that at all.
It got stuck on the cable carrier, but then the eye came in.
Yep, it got stuck. It said, hey, I'm turning. I'm supposed to be slowing down as I turn, right? And then it all of a sudden got stuck on that cable carrier. And it said, I'm giving 23% power to the motors, but it's not enough to get over that cable carrier. Over time, the integral started getting larger, and because the integral got larger, it started adding a little bit more power to the motor. A little bit more at a time. And you'll notice that it turned very slowly, right? And then it finally straightened out to 90%. And then finished the routine where it backed up, lifted up the motor, and went forward and dropped the cube, right? That's how you can use I. I is used to overcome things that are unexpected. D is for clamping down. It will slow down. It will allow for not as fast change. We typically don't use D. Tuning is a pain. Lydia can tell you that. Drew and Annie will learn it. So let's hit our next slide.
We got 1 minute.
Yep. So when we come back, we'll talk about PID loops and flywheels, but we've kind of already talked about this, so we'll go quickly. We're now going to break. We're going to break for lunch, so why don't you guys get washed up? Are we ready?
No?
So what do we remember from PID loops?
Phones away, and by away I mean in your pockets. What about in your pockets? If your pockets zip, zip your pocket. Not that most pockets would zip.
So how do PID loops work?
That's not a pocket.
It's technically a pocket.
Anybody who's not on programming? PID loops, how do they work? I just gave a whole lecture on it.
They just work. So they take interval, or they take proportional intervals.
And derivatives, so let's just talk about the proportional.
It's error over time, and it has a large error at the start, but it goes down as it tries to reach its goal set. And once it reaches that goal or set, it'll kind of like do a wave motion around it because it keeps releasing power, and then has to give power to it.
Yep. Now, why would I use integral?
In case it runs into something, and then it will proportionally add in more and more power to it.
Yep. All right. Gabe was paying attention. So, if I had a flywheel and I had a requirement that I had to spin at 3,000 RPM, and the initial state is not spinning, the error would be what?
3,000.
Yep. And I could use proportional to get close. So, next slide. So, power is going to equal P times error, right? We just talked about this. What happens when the error is 0?
It's directed.
How much power do I send to the engine, to the motor then?
0.
So therefore, what happens?
It will.
Well, I mean, it has momentum because it's a flywheel.
Increase error because it is going.
What happens when the error is negative?
It will release. It will give more. Release power.
It doesn't release, but it gives power what?
A whack.
Go the other direction. Very good. All right, next slide. So we have, when we talk about integral, we talk about total error, which is the area under the curve, right? So what happens when error gets to 0 if you're using integral?
The area, or is it?
Total area, remember. So,
Is it still technically increasing, or is it?
well, let's say it gets to 0 and just sticks to the line.
Then the area just stays the same.
That's right. And so we just have constant power, right? If the area goes negative, what happens?
The area would decrease, or does it?
The area would decrease, and until it gets negative, because the area could still be positive even when it goes underneath, right? So you can use I to give a constant state of power, though you've got to watch out for something called integral windup, where you give it too much power, because integral will rapidly add power, and you have to be careful with that. And then we have D. So D is the change of error. Do you guys know what a tangent is on a curve?
It's when somebody goes for a long.
Yes, it is that, but it is also a point on a curve where you can run a straight line through without touching any other point. And you can get the slope of that. And when that slope increases, you know that your change is happening very rapidly, right? So we can control the change at which we apply power by using D. So if it's changing too rapidly, we can increase the D and it will slow it down, so it doesn't change as rapidly. Does that make sense? It can lead to a more smoother transition. All right. Next. All right. So we use PID loops in a lot of different things. So one of the things that we will use it for is we will use the limelight to do targeting. Okay, and we will target detected April tag on the limelight. So for example, if this is my field of view on the camera and I see an April tag over here, and this is center where I want it, the limelight will tell me how far off center it is. So what does that mean? If center is where I want to be, which is 0, and I can tell how far off center, whether that be positive off center or negative off center, what am I calculating there?
Error.
Who said that? Oh, the error, right? And what would I control on the robot to get this on center? What could I control? If it's a swerve bot, what could I control? If it's a swerve bot. If I had a turret, what could I control?
The turret.
But let's say I don't have a turret and I have a swerve bot. What can I control? The drivetrain. Take a look at the watch. What's happening as that's going sideways? We're strafing, but what are we also controlling as we go by? Exactly. We're rotating the robot as it strafes to make sure that it stays, to make sure it stays on center of that April tag. So that's one way we can use PID loops very easily, very quickly. You can do a lot with PID loops. Next slide.
Hold on. There we go.
So here is an entire auto done with all PID loops. Everything you see, every motion you see here is being controlled by PID loops. All of this. Everything there was controlled by a PID loop. The height of the elevator, we calculated the distance on the height using the encoder. So how many rotations we had to go to get to a certain height to be able to deliver. The arm shooting out, again, encoder, determining how far we have to shoot out, coming back, dropping down. We calculated distance by how much we turn the wheels on the drivetrain to go over that ramp, coming back. We did the same thing. And then you'll notice it did that very slow climb. That was using the gyro to tell us how off kilter we were. And it solely used that to correct the error of the angle of the gyro. So if we were a rookie team, we could be doing a whole hell of a lot with PID loops, and we do a whole hell of a lot with PID loops. This robot almost took my hand off too. So, literally. Next slide. So, another thing that we use is trapezoidal profile. Trapezoidal profile can be used for elevators. It can be used for motion of the robot as well. It can be used for any mechanism where you have an acceleration, a constant speed, and a deceleration. It's very similar to a PID loop, but instead of controlling the distance, the error that you're controlling is how quickly are you accelerating. So we can measure acceleration of a mechanism, right? So if I want the acceleration to be, I don't know, 0.1 meter per second, I can measure that, and I can adjust how much power I give to the motor based off of that, right? I can then measure a constant speed, and I can adjust the error based on that constant speed by doing very tiny little PID loops, and then decelerate. Here, if you look at this, this is us using a trapezoidal profile to go a set distance.
Yeah.
Let's try that. It came up.
Maybe, hold on. Let me just turn this off.
Why do you have that?
That might help though.
Maybe.
What do you have against YouTube Shorts?
What don't I have against
That's
Specifically block it.
Let's try this again.
Is it also maybe hiding the advertisement? No.
I want to open it in like a guest tab or something.
Or an incognito window? Do your things run in incognito?
I don't think so. Let's try Google Chrome.
Why are you so zoomed in?
Yeah. This is what Google Chrome looks like on Linux, right?
Oh.
So this is using a trapezoidal motor so here, watch. It accelerates, goes at a constant speed, slows down, re-accelerates, constant speed, slows down. Whereas what happens with a P-loop? If
It'll wobble back and forth.
if I am at 0 speed and I need to get to a certain speed, what happens?
It accelerates quickly.
It accelerates very quickly, right? This controls that acceleration. So it's a nice smooth acceleration, constant speed, and a smooth acceleration down. This is the thing that Nate always wants us to do that we never get done. But
Wait, was that in the college?
that was in the college. That was
They let us practice in the college.
at one time. Now they let us practice in the college again.
Today?
A few weeks ago. So it's a long, complicated story. Another method that we use is current limiting or constant current. So the current limiting, what it will do is it will measure the current, and if it sees a spike in current, it will stop sending power to the motor. Why would we do that? Anyone on this half of the room?
What happened?
Why would I measure the current, and if I saw a spike in current, stop sending power to the motor? Why would I do that? Yeah, so we don't break the motor, so it doesn't stall. And we have mechanisms. Sometimes we'll build mechanisms. For example, let's say I have 2 motors here, and I'm taking something in this way, and when it hits this backdrop, those motors could still be spinning. Do you think the driver or the operator can see this top-down approach and how far something has been pulled into the robot?
No.
So we use current limiting to prevent stalling of the motor so that we can pull in rapidly and then stop sending power to the motor to keep them from breaking. Conversely, we can do a constant current. Why would we do a constant current? Anyone on this half of the room? Why would I want to constantly send power to a motor?
So that it doesn't just drop it, it keeps it in and it's still gripping it, but it's not like breaking loose.
Exactly. So for example, this year with the algae intake, we had, it would pull it in, right? And it would constantly give a little bit of power to the motor just to hold it in. And it would also make that horrible sound. Have you guys heard the motors do that high-pitched sound before?
Maybe.
That is the motors telling us you're doing something wrong, but we're not listening. But it also allows us to hold on to things tightly.
And we choose to not listen.
And we choose not to listen. It's one thing if we hear that noise and we're not expecting it, that's a problem. If we hear the noise and we're expecting it, that's okay. So LEDs. We've put LEDs on the robot pretty much every year, but we've never really used them like we used them in 2022. So in 2022, we had various, let me see where we are. If you watch the match, where are we? Here we are. If our robot had a solid blue, it meant, was it solid blue or, do you remember, Lydia? Were you there? Let me see. Well, we'll watch for a minute. So if we had, that is it. If we had it blinking blue, it meant we had 2 balls in the robot. If it was solid blue, we had 1 ball in the robot. If it was yellow, we had nothing in the robot. It would turn green if we were targeted on this. You'll notice that we have this turret on the top, and it's constantly targeting that. And then when it doesn't see it, it scans. Do you see how it's scanning going back and forth? So then when it catches it, it then turns. So we have 2 balls in the robot. They run over to here. Eventually it will turn green, and then they shoot them in. Really good feedback to the driver and operator. They can see exactly what's going on in the field. They do not have to take their eyes off the robot. They can see, oh, it's solid blue. I've got a ball in the robot. Oh, it's blinking. I've got 2 now. Oh, it just turned solid green. I'm targeted on my target, and if I shoot, I'll be able to make it.
Will, you're missing one.
I am missing one.
Oh, come on, Mr. Will.
Do you want to, if you can find it.
I know what one it is.
And then we have our final one, which is party mode, where we just had the robot go all sorts of different colors because we started climbing. And you can see over here, you see our operator Ben doing it, and you see our mentor Seth doing a little dance, and you see Nate jumping like crazy because we just won the match, and this was when we won finals at Ben Salem. So
There was a lot of points that game.
there was not. I mean, so they went crazy. But yeah, Ben had this very stoic, very serious look on his face as he would be climbing the robot. Seth would be like sitting there being like dancing away. I can't dance like Seth, don't expect me to. But the only thing, yeah, and that was actually a little myth and lore. When we lost the first match to Redbird, who we were playing in that match, the driver on their side tore off his shirt like he had just won the whole thing. And our side was like, all right. You lose your shirt, that's fine. And we came back and beat him 2 times in a row.
Wait, like his.
He's his jersey. He ripped off his jersey.
Maybe somebody didn't tell him that it was a best 2 out of 3.
That's what I wondered. Like, so the other 2 teams that we were with, I believe it was Mercury, but we were also with, does anyone know?
Wait, the teams that we were with in
That year.
2022? That was Mighty Monkey Wrenches and
Thank you. It was Money
Retro.
and Retro Robotics. Do you guys know who Retro Robotics is?
Good team.
Good team. We like to hang out with them. Yeah, I remember we got into finals. First round of finals, Rizzo comes up to us. Do you guys know who Rizzo is?
No.
He's an announcer. He's pretty famous in FRC. You'll get to know him. He stops by the shop occasionally. Rizzo comes up to us. He's like, listen, I don't know if you guys noticed this, but in the first round of finals, we were the team with the highest score. I think we can win this. And we were like, what are you talking about? You are crazy. And then we won again, and again, and again. And we won the whole thing. Sometimes just believing is enough to win the entire thing. And our drive team believed after Rizzo talked to them. And we won the whole match. It was fantastic. So, next slide. So we use LEDs in that way very much. So, swerve. We are all familiar with swerve, right? It allows us to like go downfield while we're turning like this and do all sorts of crazy things. So, for those of you who have not driven swerve, we basically do, this is standard on a lot of game controllers too. Forward, back, strafing right and left with rotation on this. The question is, how do we do it? Mathematically, how do we do it? Does anyone know? Next slide. We do it with vectors. Does anyone know what a vector is? Can someone give me a definition of a vector?
Longitude and latitude.
Nope. Mark. I mean, theoretically, I guess it could, but that is not what the definition of a vector is in physics.
Something that can represent both direction and magnitude.
Correct. What is magnitude in our case?
No clue.
Hannah? Direction and use another word for magnitude. Speed. So, we have 4 wheels on the robot, right? For swerve. Each are given a power independently of one another, right? Each can turn independently of one another. So each wheel will have a vector and a magnitude. So hypothetically, if we were going forward at 10 meters per second, which way would all the wheels be facing? If we're going forward 10 meters per second, which way are all the wheels facing? Forward. What speed are all the wheels doing? 10 meters per second. Pretty simple. So you can imagine if I push the joystick forward, this is the configuration it's going to be, right? If we're doing, we should also talk about the fact that the robot, that swerve can both be field oriented or robot oriented. For our purposes, we do field oriented. So if I press the robot forward, all the wheels will face away from the driver and it will move away from the driver. Does that make sense? So if the robot is like this, and this is downfield, the orientation of my wheels will be like this, right? Because it's going away from the driver, because that's which way forward is. How do we rotate the wheels so that they're facing the right way? How is that done? What? Motors. But how do we control the motors so they get to the right position? What mechanism do we use? What did we just talk about for an hour before lunch? Gears, right, but what? PID loops. So, hypothetically, if my wheels are facing this way, and I want it to go that way with the controller, what is my error? 90 degrees. Gotta turn every wheel 90 degrees. And I use a PID loop to do that, to control how the direction of my wheels face. If I am at 0 and I want to go 10 meters per second, what am I going to use to get up to 10 meters per second? PID loop. So I think it makes sense that I could use a PID loop to get the wheels to face this way. If I want to strafe, right, I just turn the wheels using a PID loop 90 degrees and strafe, left or right. Make sense? If I want to turn in place, what is the orientation of my wheels going to be? If I want to turn in place, and then I send power this way, this way, this way, and this way. Does that make sense? And then that will spin my robot in place. So if I want to go downfield and spin as I'm going downfield, how do I do that? How does that work? How does it work that I could be spinning and going downfield? What's going on there? So in theory, I have 2 things going on, right? I've got a robot that's going downfield, and I've got a robot that's spinning. How do we even begin to calculate that?
2 different controls.
Well, yes, we have 2 different controls, but I mean, how do I move? If my wheels are in this configuration to spin, for spinning, and my wheels need to be in this configuration to go downfield, which configuration do I pick? Not quite. What we do is we use something called superpositioning of vectors. I can calculate where I want to put my wheels based off of two vectors. So if I want to go downfield and I'm looking at this wheel, I can calculate the position based off the magnitude. The magnitude will be how long the arrow is, and the way it's facing is its direction, okay? So if I was going down with full speed, this could represent full speed, and let's say I was turning at half speed, so that'd be half this line. Does that make sense? I can calculate a new vector, and this new vector would be here, so ultimately I would slightly turn the wheel this way, not straight, but slightly to the left. Does that make sense? With a lot of power, because it's a very long line. I want to calculate this vector. So I'm going full speed and I'm going, okay. So I calculate again. I figure out this vector. So I turn the wheel to go, this is slightly more, this is slightly less. I want to calculate this one. So now I'm going to orient my wheel this way and send power that way. I want to do this one. So it's close to that. What ends up happening is I learn how to position my wheels by taking the two vectors that are dictating what my position should be and the speed I want to go at that direction. So, you know, if I'm looking at rotating and I got power on wheels like this, and I want to also send power to this, I can put these vectors together. It's called head to tail vector superpositioning, where you connect your two vectors and then you draw a new vector that represents a new magnitude with a new position, with a new angle. And then we can calculate that on here, and that allows us literally to go downfield while spinning. The guy who did this worked at NASA. He figured this out, and he wrote a one-page paper where he left out half the math. You know, you guys have done like math proofs or where they say, hey, show all work. This engineer skipped that day at school. He did not show all his work. It is a pain in the butt paper to read because he just naturally assumes you get from like step 1 to step 25 and doesn't explain any of the steps in between. And he's like, yes, you start here and then we're here. And you're like, how did you get there? So it's a interesting paper to read. So that is how we do swerve drive. Does anyone have any questions about that? I didn't figure. You save your questions to the end.
I'm curious, so in terms of top speed and stuff, so if do you do like you would understand the proportional vectors then?
We normalize them, right.
And then is that based on
right.
Full throttle is you want to move down?
Right, so we have a full throttle, so if our vector gives us a throttle that's larger than what we can do.
Right, then you scale back.
We scale back. So really when you're going downfield at full throttle, right. you're never going downfield at full throttle while you're turning.
Right, you wouldn't have the total max.
You would not have the total, right. Yeah. So, yes, that is a good catch. Did everyone understand that? So when you do this, when you recalculate your vectors, it's possible that you get a vector that's longer than we can go, that represents a speed that we can't go, because we don't go fast enough. Does that make sense? So what do? How do I give more power to that motor to spin it while going downfield? What you can do is you can say, hey, I'm going to limit the power to this motor to this, and then lower the power on the other ones proportionally. Does that make sense? So, all right, pathfinding. How does it work? Do you guys know what pathfinding is? Here, why don't you skip ahead to the next slide? So, what are we demonstrating here? Cubes down, cubes down, cubes down. That's fine. Show it again. So what is this? Does anyone know what this is? It's an auto. Matter of fact, this is the auto we ran at Raritan. And you'll notice that map in the background were the new dimensions of the field. We actually picked that up from Mike. And we imported it into our project, into our pathfinding application. So what we do in pathfinding is we will plan out a path for the robot to follow. Does that make sense? And from that, go over to the previous slide. That path will use kinematics, which is the math of calculating what you want the motor to do without outside forces acting on it. So basically, it will use mathematics to say, oh, you want me to follow this path at this speed, and it will say, oh, well, if I'm going to do that, What motors are you using? Oh, you're using Kraken motors. Okay, you're using Kraken motors. You're using a swerve drive. Okay, I got that. I'm going to do all the mathematics behind the scenes to say, to do this, you have to accelerate at this speed. You have to go to this point. Okay, I can follow that point. I get to that point, then I got a curve to go over to here, and it will calculate all the math for us. We do not do that calculation. That calculation is painful.
Is pathfinding only for auto?
No, it does not have to only be for auto. And I'll explain that a little bit. So theoretically, any motors that you're running can do pathfinding, but typically we use it for auto. And we did use it not in auto this year as well. We did on-the-fly pathfinding, and I'll explain that in a little bit. Odometry, so while kinematics will give you kind of the path and the plan that you're going to follow, right? What's the saying? Any good plan when it comes to war?
Any good plan that's made in war appears at the window once the battle starts.
Right, there's something to that effect, right. That's where odometry comes in. Odometry is measuring where you believe the robot is based on the movement that it has done. So if I told you, hey, take a car, jump in your car, go 25 miles an hour north for 3 hours, how far north would I be?
75 miles.
Yes, we'll assume that I can go 0 to, there's no acceleration, I just start, okay? Make it simple. 75 miles north, okay? And I say make a right turn, and now I want you to go 1 hour at 30 miles an hour. Now, how far north and east am I? I am 75 miles north, and how east am I? If I made that right. What?
105 miles, but you're 30 miles.
I'm just 30 miles east, right? Because if I go 1 hour at 30 miles an hour, I'd be 30 miles east of my position. Wow, not taking the 75 miles, 30 miles. This is X. This is Y. Could you calculate the position of Y, knowing that information?
To calculate y from x, from the start.
Well, let's say this was 0, 0.
And you want me to calculate the straight shot to y?
Not the straight shot. I just want you to calculate the position in miles from X.
Miles from x.
Well, actually, is it XY? Yeah, it's XY. That would be the position of Y, right? 75 miles north, 30 miles east, right? So knowing how fast I'm going and how long I've traveled, I can calculate my position. That's what odometry is doing. So the odometry, it's measuring the robot, it's reading in the motors, it's knowing how fast the wheels are spinning over time, and it's calculating our position on the field. When we determine position on the field, the way we do it is, do we have blue? Oh, we do, look at that. There's a blue side and a red side, right? So here's the blue side of the field. Here's the red side of the field, right? The way we look at the field in pathfinding is this lower corner down here is 0, 0 in meters. Aiden, do you know how long the field is in meters?
Oh God, no.
Let's say, yeah, I think it's like 127 feet, right? That seems,
No, it's like 50 something.
It's like,
yeah, I don't know. But
It's about 30 by about 60. With a little less.
right, but I mean, you guys can imagine, if I was right here, I'd have some meters by meters, right, from this position. If this was, right, like you get that. If I'm here, I have some meters from this position, and I can calculate a Y and an X in meters of where the robot is on the field. Well, Path Planner, which is the application that we use with Pathfinder, does that. And then as we move, odometry updates based off of our starting location. So we have a starting location at X and Y, and it just keeps updating based on how we move, where it thinks we are. How good do you think that is? Be honest, how good do you think the robot is at measuring where we are on the field using speed and rotation and all of that?
Bad.
It's actually, yeah, I mean, it gets it to be like 3 to 6 inches off. So if you're trying to get really precise, 3 to 6 inches can be a lot. If you don't have to be precise, is 3 to 6 inches a lot? Not really, right? So it depends on how accurate you have to be. This game, we had to be super accurate, right? So 3 to 6 inches off would not get us on the reef. So how do we correct for that? How do we fix that?
Our limelight.
Correct. And that is pose estimator or pose estimation. And what we do with pose estimation is we use a third means by which we calculate our position. And so if kinematics is where I should be, odometry is trying to measure where I am, pose estimator is going to figure out where you are. Does that make sense? So it could be like a GPS unit. Like if I had a GPS unit on the robot that was super accurate, I would know exactly where I was on the field. In our case, we're using the limelight and we're using known positions. What are those known positions that we're looking at?
April tags.
April tags. So in our code, we have programmed where every April tag is on the field. And when we see one of those April tags, we reference that and we say, oh, I see on the limelight some April tag and it looks like this on my limelight. It's skewed, right? Does that make sense? It's skewed because it's on the side. So I can say, oh, it's skewed at this angle. So it's this far off of center. It's this big on the limelight. I know how big it's supposed to be. I know how big it's supposed to look like on the limelight. From all that information, I can calculate. So if this is the robot and it's seeing an April tag right here on the field, I can calculate from this limelight to this April tag where I am. And I can use that math to determine my X and Y on the field. So that will tell me within an inch of where I am. And so once I see where I actually am on the field, and the odometry is trying to follow the kinematics, it's thinking it knows where it is. The pulse estimator will tell you exactly where it is, so it will correct the odometry and say, oh, you thought you were at X, Y, you're really at A and B. Let's correct slightly to get back on path to the kinematics.
The farther away you limelight instrument April tag, does that have anything to do with how precise it will be?
Yes, because the further away, the harder it is to see. But generally speaking, if we're looking at half the field, we're going to get a really good estimate of where we are. If we're looking at if we're over here looking at an April tag over here, that's when it gets a little dicey. But you'll notice that April tags were all over the field. So I just have to see one April tag and I know where I am on the field. And because I know where I am on the field, I can then correct my odometry and I can make slight corrections to match my path, which we're calculated with kinematics. So that's why it's called path finding. You're following this path that was planned out for you. And the odometry is trying to follow that path. And then all of a sudden, the limelight's like, oh, you're off path. So it slightly swerves you back on the path. And that's how we get really precise accuracy.
If the robot can find itself through the post estimation, then why do we have to reorient?
Because we're not there yet. You are not wrong. We could hook that up. That's a good question. Because we just hadn't had time to look at it. But yes, we should be able to do something like that. So why? Because I don't think we can, the problem is I don't think we can set the gyro. I think we can reset the gyro, but I don't know if we can set the gyro. We just didn't do the calculations. But you're right, we should be able to do that. Well, I know why. There's another reason. We don't get our post estimate, we don't get our rotation based off the post estimation. We use the gyro entirely for that. Because the rotation is weird.
When we weren't oriented right, we would have that check.
Yes. Yeah. So, yeah, actually that's exactly why. Because the setting the orientation of the robot on the gyro was a pain in the butt. And it didn't work real well. So that's why it became a manual process. All right, so back to here. If we play this again, so what we do is we make a path. You'll notice all these little event markers, these little gray things. Those are where we're running commands on the robot. So when we hit that event marker, we're running a command. You'll notice that, actually if you can pause it, you'll notice that there's an event marker in front of each post. What do you think is happening?
Every event marker gives the robot a position and a rotation that it has to be in, and then when it's going to the next event marker, it'll
No.
It's telling it to shoot out.
Right. So each event marker is us giving the robot a command to run. So you'll notice that there's one here, 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 and here. Event markers. So when we get there, what happens is the path will stop, run the command, and then when the command ends, it will then proceed to run the path again. And we have ways to say, hey, stop. We also have ways to say, hey, don't stop, keep running. So these here, these event markers here coming off of the, actually it's these three, coming off of the player station. What do you think we're checking at those points?
If we have coral,
Not only if we have coral, but what?
if we have algae too.
Nope. Specifically, it has to do with the coral, but where would the coral need to be? In the end effector. If the coral's not in the end effector when we get there, where do you think the coral is? Where could the coral be? It could be in between in the elevator, right? So we have a decision point there that we were trying to get programmed so that if it was in that decision spot, it would stop the robot. I don't think we ever quite got that far. But the idea was we were checking to see where the coral was. When we get here, we run the coral. And you notice when we run this, it just runs the whole path. There's no stopping to deliver coral because that's what these mean. And you'll notice in teleop, we ran that same command to deliver the coral that we ran in auto. Does that make sense? So next, so then you can see what it looks like here. So here's the robot. And you'll notice that it never crosses the tape. That is a well planned out path. Now, if we hit next slide, limitations and basic strategy. Pathfinder and path planning only works if we have a well-built robot. You notice how the robot kind of did a little wobbly thing at the end?
Yeah.
One of the limitations for us in pathfinding this year was we couldn't lift the elevator up as we were driving. Why was that?
Because the weight on the top of it will make it wobble back and forth to a point where we could tip over.
Exactly. There were teams that once they got the coral in at the player station, they lifted their elevator to the top position and came into the reef at full speed to deliver it.
Right.
And if we could have done that, do you think we could probably have gotten a 4-piece coral? Our robot this year could not do a 4th-piece auto. It was mechanically impossible. Does that make sense? Like there was, short of redesigning the robot to do things that it can't do currently, we wouldn't have been able to do it. We can only do autos that the robot allows us to do. And that comes to design, that comes to mechanical. If design doesn't design it, if it puts too much weight at the top, there's nothing we can do about that. Right? We're gonna have to go all the way to the coral, all the way to the reef before we lift it up, right? And lifting it up is a half a second. And bringing it back down is another half a second. That's a full second. And we're doing that 3 times. That's 3 seconds in a 15-second auto. That is a fifth of the time in auto. Just upping and lowering the elevator. That's a lot of time, right? So we can't do something if it's not designed to do that. If it's built shoddily, so loose bolts, loose gears, that odometry that I'm talking about, it's going to be slightly off. If gears are skipping, it's going to think it's completely somewhere else than it really is. And even with the limelight, it's not going to be able to correct. The limelight allows for subtle corrections. It allows to correct like 1 inch to maybe 3 inches, which is perfect, which is what we needed, right? We're just being, odometry gets you within 3 to 6 inches, right? So if we can correct that 3 to 6 inches, which, post estimation will do, we're great. But if it's more than that, we start running into problems. It will start correcting, but it won't correct enough by the time it gets to the target. Does that make sense? The other thing we have to be careful of, we want to do curves rather than sharp lines. So if I'm doing, we didn't have that benefit this year because we had to stop at the human station to deliver. But if I can do this as opposed to this will go quicker than this because this makes me come to a complete stop, whereas I keep constantly moving with that. Does that make sense? So when we're designing our paths, we like to design with curves to keep moving, to never slow down. All right, we're almost done, almost done. Lastly, if wheels skip, and this does happen when you hit things, your estimations will go off. Next slide. Okay, this is the last slide. Okay, second to last slide. Because the next one is it showing it. So we delved a little bit into artificial intelligence with object detection. So do you guys know what a neural net is? Have you heard the phrase neural net? So a neural net takes inputs, does some calculations, and outputs basically classifications. So it can classify things. It will look at something and say, oh, that's a piece of coral. Oh, that's a piece of algae. And it can also, with our limelight, tell us how off-center that coral or algae is so that we can correct and follow it. Does that make sense? So by using a PID loop, with knowing how far off-center, we can track coral. Did you see how that happened? So it found it and then just started following it. And we said, hey, follow at a distance of 1 foot. Don't touch it, just follow it at 1 foot. So that is algae tracking. And next slide, I think that should be it. I don't think I have anything else after this.
Yep.
That's it. All right.